Hello everyone, this is Mr. Underkoffler, and today we're looking at the guided notes called Probability Simulations. Alright, follow along. A simulation is a way of modeling one or more events of a probability situation. Simulations often model events that would be difficult or impractical to perform. Anything can be used as a simulation, but most people will use items that are easily accessible, such as coins, number cubes, spinners, marbles, or maybe even pieces of paper mixed together in a hat. The key to choosing a simulation is to make sure the number of outcomes, this is key, ladies and gentlemen, is to make sure that the number of outcomes of whatever you use, whether it's coins or number cubes or spinners or whatever, is the same as the number of outcomes of the real thing. So let's look at some problems. We're going to circle the answer choice that's correct for each problem. Okay, problem number one. There are 6 possible toys in kids' meals at a fast food restaurant. What could be used to simulate the chance of getting each toy if they are equally likely? Okay, here's the whole thing you got to pay attention to. There are 6 possible outcomes, and they are equally likely. So we need something that we can use that has 6 possible outcomes, where each outcome would be equally likely as the other. Would flipping a coin have 6 possible outcomes? No, that would only have 2. Would rolling a tetrahedron have 6 possible outcomes? In case you forgot what a tetrahedron is, it's kind of like a die, except it only has 4 sides, so no, 4 sides would not be good for 6 outcomes. Spinning a 4-space spinner, again, no. We need something with 6 outcomes. Rolling a number cube, yes, that has 6 sides, and each side is equally likely to show up whenever you roll it. So that's the kind of thing we have to pay attention to when we do these problems. Now, I'll be honest with you. Number 1 was the easiest one on this page. Not that the other ones are necessarily that difficult, but some of them do take a little bit more thinking, especially once you get to problem number 3. So I would like for you to try 2, 3, and 4 on your own. Again, we need to make sure that the number of outcomes of whatever we pick to use is going to have the same number of outcomes as what we need for the real life situation. So hit pause now, do 2, 3, and 4, and then hit play once you're ready to see how you did. Okay, have you already done numbers 2, 3, and 4? Problem number 2. We have one of 8 possible trading cards showing up in these cereal boxes. Flipping a coin? No, that only has 2 outcomes. Flipping 2 coins, 2 times 2? No, 4 outcomes. Flipping 3 coins, 2 times 2 times 2, because each coin has 2. So 2 times 2 is 4, times another 2 is 8. Yes, that actually would work. So if you were stumped on this problem, you forgot that you would take the number of outcomes and multiply it to each other. So 2 outcomes for the first coin, 2 outcomes for the second coin, and 2 outcomes for the third coin makes 8 possible outcomes. Rolling a number cube, no, that would only have 6 outcomes. Problem number 3, we have a free throw percentage of 80%. Now you need to know that 80% means 80 out of 100. And 80 out of 100 could reduce to 8/10 or 4/5. So if we could somehow get something with 100 outcomes would work, but that's kind of insane. Maybe something with 10 outcomes, because this can reduce to 8/10, or 5 outcomes, because this would reduce to 4/5. Flipping 2 coins, that only has 4 outcomes. And if 2 tails is the missed free throw, but every other combination, which would be 3 of them, is the made free throws, well, 3 out of 4 is 75%, so that doesn't quite work. It's close, but not quite. Spinning a 10-space spinner, where the numbers 1 through 8 represent the made free throws, numbers 9 through 10 are the missed free throws. Well, that would be 80% are made, 20% are missed. That's exactly what we need. Rolling a number cube, numbers 1 through 4 makes the made free throws, 5 and 6 is the missed free throws. Well, that would be 2 numbers out of 6 that are misses. 2 out of 6 is 1/3 or 33%. 4 out of 6 is 2/3 or 66.6 repeating percent. Not quite 80%. So no, that's not going to work. Problem number 4. After a victory, a video game rewards the player with one of 4 possible rewards. Okay, so notice we have 4 possible rewards. Don't pay much attention to these numbers here. Yes, I know they're different numbers. I know you might be tempted to add these numbers together and think it should be out of 10, and therefore you're going to pick choice C. But no, it even confirms it. There's a 25% chance for each reward. Well, that's because there's 1 out of 4 possible rewards. So we're looking for something that has 4 possible outcomes, and that would be flipping 2 coins. Not 8 marbles in a bag. That would be 8 outcomes. Not a 10 space spinner. Not rolling a number cube. Now, actually, you could use 8 marbles in a bag if there's 4 different colors, because then you'd have 2, 2, 2, and 2. And that would actually reduce to the idea of 1 out of 4. So believe it or not, choice B could work. It's not the obvious choice. So this one kind of had 2 different possible answers. But choice A is the most logical choice. Okay, problem number 5. Let's read this together. A local grocery store sells cereal in 2 packs for a special price. The probability of a box containing a prize is 1/3. The spinner shown was used to simulate the chances of getting a prize, where blue represents the success, and each red space represents a failure of getting a box that contains a prize. Since the cereal is sold in 2 packs, one trial consists of spinning a spinner twice, and that's because we're buying 2 packs of cereal at one time. Suppose 10 trials are done. And ladies and gentlemen, if you look here at this table, here are the results of those 10 trials. Using the results shown in the table, what is the experimental probability of selecting a 2-pack where both boxes contain a prize? That, ladies and gentlemen, is key. Because if you thought that only 1 box is what this problem wants, no. We want it so that the 2-pack where both boxes contain a prize. And that's why you can see here on this table of results, only this one here had both boxes giving a prize, and this one here as well. They were the only 2. So we're going to write this probability as a fraction in simplest form and as a percent. So that's 2 different situations, two of these 2-packs that gave us a prize out of 10. So there you go. Now, it was actually using the spinner, okay? But, and that's why it had to be spun twice, so that way it's a 2-pack, not just 1-pack. All right, let's reduce this. This gives us 1/5, which is 0.2 as a percent. That would be 20%. Go ahead and write that down if you have not already. Okay, I would like for you to read and do problem number 6, and then read and do problem number 7. Hit pause, do both of them, take your time reading them, show your work, get your answers in whatever forms they ask for the answer. 6 and 7, hit pause now, and then hit play once you're ready to see how you did. Okay, have you already done problem number 6 and number 7? If you have not already done them, you need to hit pause now because I'm going to go over them. So, problem number 6. We checked out this table and we are looking for the experimental probability that a repeat customer receives a gift card 2 days in a row. So, which ones are receiving the gift card both days in a row? Well, this one does. This one does. Not this one. Not this one. This one does. Not any of these. And not that one either. So that's a total of 3 of them out of 10. And that would be 0.3 or 30%. I don't know if you probably don't even have to make it 0.3. You probably already know 3/10 is 30%. So if you don't want to show the 0.3 in between, fine with me. Okay, finally, problem number 7. We have this computer simulation, and we are trying to find the simulated probability. Now, that's a fancy way of saying experimental probability, but whatever. It was from a simulation, so fine, simulated probability. As a decimal and as a percent. So they're not asking for it as a fraction, but they do want it as a decimal, and that actually makes sense. If you look at the relative frequency scale over here, we are counting by every 500ths, and these are decimals, so that makes sense. And we are trying to find the simulated probability of it being 8 or fewer rolls that are needed to obtain all the even numbers on a number cube. So we need the bar graph for the 8 or fewer, so also the 7 and also the 6. So let's write these down. The 6, hopefully you had 0.08, but we're going to add that because the word or means you're going to add. We talked about that many times with probability. The 7 was 0.2 and the 8 was 0.12. If you add these together, your probability as a decimal will be 0.4. As a percent, that is 40%. And that's it. This page of guided notes, front and back, was not meant to be very long. Thank you for watching. We'll see you next time.